So in this video, I'm going to be deriving an expression to model the change of height of fluid in a tank with respect to time. And so for this problem, the tank is going to be sealed and there's going to be a little hole in the bottom where the fluid is draining out. So before I get into that problem, I'm first going to talk about the scenario where the top of the tank isn't sealed, because that's a little easier and it'll help us conceptualize what we need to do for the problem with the sealed tank. So we're going to start with a tank that's open, and there's a little hole in the bottom, and there is fluid leaving this hole. So we have an initial fluid level that's in the tank. I'm just going to call that H. And then from here, we can go ahead and start to apply Bernoulli's equation. So to do that, I'm going to go ahead and define 2 points. So the first point is going to be up here at the top of the liquid level, and the second point is going to be down here at the hole, like right at the edge of the hole where the liquid is leaving. And so I'm just going to go ahead and write down Bernoulli's equation, and then we'll go from there. So in this problem, we're going to go ahead and ignore frictional heating. And so the right side of the equation is just going to be 0. And that simplifies the problem a little bit. We will have to incorporate it in our expression later on. And so basically the goal of this is we want to find an expression for V2. Because once we find the expression for V2, we'll be able to get the volumetric flow that's coming out of the hole, and we can use that to model the change in height in the tank. So I guess our first step is we need to define the 2 different pressures. Well, P1 is easy. It's just open to the atmosphere. P1 is going to be atmospheric temperature, or atmospheric pressure, 1 atmosphere. Right, it's open to the top of the tank, or the top of the tank is open to the atmosphere. So the pressure at the top of the tank is just going to match the atmosphere. Now, for the pressure at point 2, one way to think about it is we have a sudden expansion. And so the liquid rushing out of the tank goes from a very small cross-sectional area to basically a large one outside of the tank. And so when there's a sudden expansion, there's no time for pressure to recover. And so the pressure at this point, P2, is going to be equal to some pressure out here out of the tank. And so again, since we're back out of the tank into the atmosphere, P2 is just going to be equal to atmospheric pressure. So P1 is atmospheric pressure, P2 is also atmospheric pressure. So these 2 terms are equal. So now when we come back to our Bernoulli's equation, we go ahead and plug that in. It's just going to cause this whole first term to go to 0. So that simplifies it a little bit. And now we'll go from here and take a look at the velocities. So the velocity at point 2 is what we're trying to find. So how do we model the velocity at point 1? Well, the tank has a very small hole, so the volume that's leaving the tank isn't going to change the height of the tank too much. And so the velocity of this kind of top level moving down is going to be extremely small. And in this problem, we're just going to say it's negligible, and just to simplify things a little bit. So V1 is going to go to 0 because, again, it's super small, and it's not going to change our equation too much. So now we need to look at the term that represents the change in potential energy. And so then just for Z2 minus Z1, our Z2 is going to be 0 down here at the bottom of the tank, minus the top level of the tank, which is just H. So this is going to be 0 minus H, or negative H. And now from here, we can go ahead and solve for V2. So if I move this term to the other side of the equation, we're left with V2 over 2 equals GH. And then this is super easy to solve. We just have to multiply by 2 and take the square root of both sides. So this is the expression for our for the velocity at point 2. And so then from here, what we can do is we can model the rate of change of the height, or we can model the rate of change of the volume of the tank with respect to time by just finding the flow that is coming out. And so to get this volumetric flow that's coming out, it's just going to be the velocity at the hole times the cross-sectional area of the hole. And so from here, we can use that volume is equal to the cross-sectional area times the height. And in this problem, cross-sectional area is constant. So it's just going to be the cross-sectional area times the change in height with respect to time, going to be equal to the flow coming out of the tank, which is the velocity at 0.2 times the area. And so basically all we're going to do is the same thing again, keeping this end goal in mind, but we're going to seal the top of the tank. So I'm just going to kind of draw a top and erase some of this. I'm going to rewrite this expression back at the top to remind us where we're going. And then we'll start to work on this problem. All right, so again, we're going to kind of define the same 2 points for this problem. So point 2 is going to be the hole where it's leaving the atmosphere, or leaving into the atmosphere, and then point 1 is going to be the air at the top of the tank, or this area at the top of the tank, the very top of the fluid. And so kind of similar to last problem, I'm going to start with writing down Bernoulli's equation. And we're going to assume that the frictional heating is 0. So kind of starting how we did the last one, we're going to find a way to represent both of the pressures. Well, the pressure at point 2 is easy because, again, nothing's changed with the hole. There's still a sudden expansion. So the pressure at the hole is going to be equal to some pressure out in the atmosphere. So P2 is just going to be 101,325. But now that we've closed the top of the tank, the pressure, this air pressure is going to be changing as we drain the tank because the volume is going to be increasing, but we have a set amount of air in there. So we have to find a way to kind of represent that. So to start, we need to find the moles of air that's in the top of the tank to begin with. So since it's sealed, there's no air leaving or entering the top of the tank, we can use the initial conditions to get the set amount of moles for this problem. So using our gas laws, N is just going to be PV over RT. And so initially, when we close the tank, the pressure is going to be atmospheric pressure. But then as it drains, it's going to change. So we can use that initial condition to solve for our moles. So we have 101,325 times the volume, which is just going to be our cross-sectional area, times this height of the air, which is going to be the total height of the tank. I'm going to call that big H. Minus the initial height of the fluid, all over RT. So this expression gives us the amount of moles that we start with in amount of moles of air that we start with at the top of the tank, and this number is not going to be changing throughout the problem. So now we can use this and use gas laws again to get an expression for P1. So P1 times V is going to be equal to nRT. And we can just go ahead and substitute this equation in here. And so that's going to be 101,325 times the cross-sectional area times the initial height, or times the total height of the tank minus the initial height of the fluid over RT times RT. So these two are just going to cancel out. Keep losing my eraser. And then on the left side, we're going to have P1 times the volume, which again is going to be the cross-sectional area, times the total height of the tank, times the total height of the tank minus the height of the fluid. And since we're modeling the pressure at any point during this problem, we're not just using the initial height. So then from here, we can solve for P1, dividing this to the other side. We're just going to have 101,325 times the height of the tank minus the initial height of the liquid over the height of the tank minus the current height of the liquid. And so the cross-sectional areas cancel, and so this is what we're left with. Now, we can go ahead and plug these values into our Bernoulli's equation. Before that, I'm going to kind of cover these other two terms like we did with the first scenario. So velocity at point 1, again, is going to be negligible. So this term is going to be 0. We still just have a small hole, so the rate at which this fluid is going down is going to be very small. And then again, we can use the idea that our 0 point is at the bottom of the tank, and h is the height of the fluid for this. So this term just becomes 0 minus h. And now we can go ahead and plug all of this in to our equation. So going to kind of erase some of this so I have room to do it. And then again, I'll start with just the left side, which I'm going to leave this term on the left side because we're solving for V2. And then when we move this over, it becomes P1 minus P2. So P1 is this term, P2 is this, so we can pull out a 101,325 over the density times P1, which is h minus hi over h minus lowercase h minus P1, or minus P2, which is just 1 times 101,325. And then for this term, since we've moved it to the other side, it will just be plus GH. And now we can solve for our velocity. And that's just going to be the square root of 2 times this whole term. So 2 times 101,325 over the density times the height of the tank minus the initial height of the fluid over the height of the tank minus the current height of the fluid minus 1 plus GH. And then from here, we can use the idea from that first scenario that we can model the change in height with respect to time using this equation. And now we have the expression for our velocity, and we're given the cross-sectional area of the hole. And so we'll be able to model this. So now I'm going to transfer over there and finish this problem. So now that we have the differential equation here from our whiteboard that we're looking to solve, we can go ahead and use Python to solve it using solve IVP. So I've imported it here, and in order to use it, we need to pass a right-hand side of the equation to solve IVP. So I'm going to go ahead and define the right-hand side. And how IVP works, it always needs to have time as the first parameter, and then the vector of your unknowns as the second one. Well, for this problem, our vector of unknowns is just the height. So we can go ahead and pull that out. And there's only one element in the array. And then we can go ahead and calculate V2 using this equation here. So V2 is going to be equal to the square root of 2 times G times H 2 times G times H times our pressure external divided by rho times times the height minus the initial height over the height minus our current height minus 1. So we have height minus our initial height divided by the height minus the current height minus 1. And this all needs to be in parentheses. What is left? Plus GH. Oh, we have 2GH over here. So I'm gonna make this, make sure my parentheses all line up. And then we need to make sure to remember to distribute this too. So I'm gonna add another set of parentheses here. And then what we want to return is the right-hand side of our equation, which is just going to be this here. So it's going to be the cross-sectional area of the hole divided by the cross-sectional area of the tank times V2. And so let's go ahead and return that. So we have negative cross-sectional area of the hole divided by the cross-sectional area of the tank times V2. And since we're using solve IVP, we have to go ahead and return this as a vector. So now I'm going to go up here, and I have a window open under my camera over here with the all the initial values, and so I'm just going to go ahead and code those in. So G, we can define our knowns. We know G, that's 9.81 meters per second. We know the external pressure, which is 101,325. We know rho, which is just the density of water. The height of the tank is 1 meter squared. The initial height of the liquid is 0.9 meters squared, or 0.9 meters, not meters squared. The cross-sectional area of the hole is 1e negative 3 meters squared, and the cross-sectional angle, or the cross-sectional area of the tank is just 1 meter squared. So now we have all of our initial values in there. We have our right-hand side, so now we can go ahead and plug this into solve IVP. So we have to pass the right-hand side to the function. We have to pass our t-span, which is going to be 0 to our end simulation time, and I'll go back and define that in a second. We need to pass our initial value to it, which is the height, supply the method, which we're going to use Redao, because this is the method that we most commonly use in class. It's the most robust, and it'll give us the least amount of errors in our calculation. And then I'm going to set dense output equal to true so that we can solve this at any point. So I'm going to go ahead and send this. Not really sure how it worked because we don't have t end, but I'm going to go ahead and supply t end. We'll say 10 seconds. And it looks like it worked. It shouldn't work. I found an error. I need to do plus. So now when you run this, it should, it gives us an error that we're getting infinity values or non-real values. So I'm going to go ahead and graph this and see if we can run the simulation time for a little less and actually get the graph. So to graph it, we can do figure 1 equals make subplots, and then we can add our scatter. Our x is going to be equal to, I'm going to add some more code to get our t-plot value, kind of the value, basically the x value for this graph, the time that we want to plot. So I'm going to make a linearly spaced array using np linspace. We're going to start at 0, go to t end, and we'll do 500 points just so it's nice and even. So x is going to be equal to our t-plot. We're going to graph our y value, which is going to be the solution to our solve IVP. So they're still getting an error, but I'll solve that in a second. I'm going to set it equal to res. Getting an error with plotting it initially, but I figured it out. So we need to plot our solution for t-plot and grab the first element, which will be where our values are. And then I'm going to go ahead and update the layout. Of our graph to just make it a little bit easier to look at. So I'm going to set the width to 600 and the height to 600, and then I'm going to set the template to Plotly dark. And so this will kind of make the graph a little easier to look at, and we can go ahead and that's not quite right. Template equals Plotly dark. We set the width, set the height. Oh, I just spelled Plotly wrong, so let's see if that was in fact the error, and it looks like it was. So now here we have our graph. And so like I said before, I had it set to 10 before. 4 works because that doesn't run too long. But if we go ahead and try to run it anything past that, like to go to 10 seconds, we get an error that the array must not contain infinity values or not numbers, not real numbers. And so immediately, I think we have a square root in our expression to compute the velocity at point 2. And so this square root must be going to a negative number, and you can't take the square root of a negative number. So the first solution I'm going to try is just taking the absolute value of this and seeing if that changes anything at all. And so we don't get any errors, but now when we go ahead and graph it, we kind of get this plot, and that is clearly not right, because we have the height is decreasing until there's no change in height, and it should stop here because once the velocity goes to 0, then there should be no change in the height, but it continues to go down. And so in order to kind of prevent this, there is a function within solve IVP. We can implement events, and basically what this event does is it's going to kind of solve this equation for us and get the 0 point so that we know when to stop our simulation. So I'm going to define another function and call it when v2 goes to 0. It's an event. We're going to go and pass our same parameters as the right-hand side to it. And then I'm just going to copy this over. So we still need to unpack our height from the array. And then now we're interested in when this goes to 0. So I'm just going to go ahead and delete this, and we just need to return this. And so that'll give us kind of our event, the time when the velocity goes to 0, and we'll know to stop our simulation there. And so then we can go ahead and type in that our event is terminal and set that equal to true so that the simulation stops when this event is reached, so when this value equals 0. And so then we can go ahead and run this and then pass it to our IVP. So the events will be equal to, and then, so solve IVP is set up so you can pass multiple events, but we're just going to go ahead and pass this event to it, our only event. So we can go ahead and run that and then look at our result. And it gives us our event termination is at this. So then we can go ahead and implement that as our t end. So we can do res.t events. And our answer is inside 2 arrays, one here and then one here. So to grab that out, we'll index in twice. And then we can go ahead and graph this. And so now The graph is now right. It's plots until our V2 equals 0, and that's kind of the relationship of the change in height with respect to time in our sealed tank with a hole.